All right, so we're going to go through the 10-2 notes. Ideally, you've taken these notes already, and you're just going to be adding some things based on this discussion. So let's get started. So I'm not going to read word for word, but I will go through the examples with the calculator here that I've got on the screen. So if you need to skip over things, pause, go back and forth, you should get used to doing that. So the whole point of this section is to compare between two means. So this is not a test for proportions when we know a certain percentage or something like that for two different samples. We're going to be looking at means just refers to something that you're measuring. So if you're measuring milliliters or heart rate or something like that, we just refer to that all as something that you can take the average of or something that you can take the mean of. So I'm going to point here with the mouse so that you can kind of see where I'm at on the notes, but basically we want to compare the means of two different samples. So it talks here about our parameters of interest are the population means. So we're going to take samples from each population and compare those. So ideally your parameter means, which are the population means, and your sample means should match up. So here I've just highlighted the notation so that you can be sure that parameter goes with population, statistic goes with sample. So we're going to compare the population of treatments by doing inference. So a reminder, a lot of the reminders I have are here in green. Inference is using the sample to make a statement about a population. So that's a really basic definition of what inference is. So we're really going to be looking at the difference between two different means. How much more or less than is one sample versus another. So in order to use these sample means for inference, right, we take some samples, we find the averages. In order to actually use that, we have to know about the sampling distribution. So if you take a bunch of different samples from these populations, what is the shape of that distribution? Because a lot of what we do is using a normal curve to estimate. So if those population distributions, if we don't know they're normal and we can't make a comment about the sampling distribution, then we won't be able to do any of our tests. So again, in green here, if we take a bunch of samples, what will the distribution of those samples look like? So here we're talking about how to make judgments about the sampling distribution. So you're going to look at your shape, center, spread, and outliers. Now, if you don't have any outliers or you don't have the data, then you can't make a comment on that. But you always can make a comment about the shape, the center, and the spread. So first of all, if you know the population is normal, then the sampling distribution is normal. If you don't know the population is normal, then you have to analyze the sampling distribution. So if you start taking samples that are large enough, that's where we get to the central limit theorem and we start talking about samples larger than or equal to 30, then we know that the sampling distribution will be approximately normal. If it's not larger than 30, then we're going to have to look at the box plot or look at a histogram and try and get a sense of those samples and if they are symmetric enough for us to use the normal curve as an approximation. So the center of, or the mean of the sampling distribution, you just can subtract one mean from the other and it'll tell you how much bigger or smaller one is than the other. And then the spread is when you calculate the standard deviation. So your standard deviation, we use the same formula for combining distributions where we square the standard deviation and add it. Now, if you look down here at the formula, we have to make sure we divide it by the sample size. That just comes from our old formulas in I think chapter 6 or 5. We're allowed to calculate that as long as our sample is not more than 10% of the population. So we've got that. Now I made one other comment over here and I said, why are these means basically the same? Now the sample mean should match the population mean. If it doesn't, then that's where we get into hypothesis testing. So we're going to assume that they match for the purposes of constructing a confidence interval or talking about the sampling distributions. So this example here, hopefully you've already read it and you already answered the question, but basically the reason that we know the shape of the sampling distribution here is because each individual sampling distribution of both the large cups and the, I believe it's medium cups, are said to be normal in the original premise. So you don't have to do anything else to know if this sampling distribution would be normal or not. So if you're finding the mean, you can subtract. So you can subtract either way, large minus medium, medium minus large. They've defined it as large minus medium. So that's what we're going to do, which is why the large is 10 ounces more than the medium. I wrote an incorrect notation here, but I left it just so you could see what not to write. Now the standard deviation, again, we use our formula, so you should be able to square your standard deviation here, that's your variance, and add them together. So you see I've plugged those in just from the problem. 0.8 comes from the example up top. Same thing with 0.5, and then these are the samples. We didn't have to check about the shape of the curve because we knew it was normal. So if these were less than 30 and we didn't know it was normal, we would have to start doing some checking. And this is something that I actually relearned when I was reading the book. You don't have to do the 10% check if the population is basically unlimited. There's, you could run this machine as many times as you want. So that check is not necessary here. So if you're going to perform inference, which means if you're going to make a confidence interval or you are going to do a hypothesis test, then there's a few things that you have to check, just like we did for one sample tests. You have to make sure that the samples are random. So just check that that's stated, or if it's not stated, then state that. You have to talk about the shape. So in this case, that it's normal or that you have a large enough sample. So either you have to know that the population distributions are normal or that they're sufficiently large. So if it's less than 30 and the population is not stated as normal, then you should use a graph, box plot or histogram, to decide if it's essentially kind of normal. So here is a little reference for yourself. If you know the population standard deviation, you're going to do a 2-sample z-test. If you don't know the population standard deviation, you're going to do a 2-sample t-test. That is your decision-making process. The 30 is really a discussion about whether or not you know the shape. So for 2-sample t-intervals, the test, well, I'll actually show you how to do it on the calculator, so I'm going to skip this part. I'm going to go straight to the example here. So the example, I'm going to talk this one the whole way through, so if you don't need it, skip it. So maybe pause for a second to read the question. I'm not going to read it out loud, but we have 2 different sets of trees in the north and south of this forest, and we're trying to see are the diameters of one tree more than the other one. So you can set up your subtraction either way when you go to compare these, whether you subtract south minus north or north minus south. And I realize I didn't leave enough room to actually write all this out, but you're really checking off for the comparison here, shape, center, and spread. So the distribution of trees I wrote here is skewed right. You can see it's a little bit skewed right. It's not a ton, just a little. And in the southern district, it looks a little bit skewed left. The mean diameter, would be larger, and the variation between these trees smaller than in the north. So that's one thing that you could compare for the spread. And then I also just mentioned that most of the trees in the south, like here, even if you look at the upper 50% of these trees, those are all bigger than 3/4 of the trees down here. Now, you don't have to make that particular comparison, but they're just asking you to state some things that are true about the distributions here. So the next part, it asks us to construct a 90% confidence interval. So I've got all my work here, but I'll just scroll down so you can see the whole thing. So first thing that we have to do is decide what kind of interval it is. And I chose a t-interval here because we didn't know the population standard deviation. So I have to define my variables. So my mu1 is the mean diameter of the trees in the northern half. My mu2 is the mean diameter of the trees in the southern half. So I happen to do north minus south when I set this up, and the book does it the opposite way, and that's fine. You just want to interpret it correctly. So I also stated what we were trying to find. We're trying to estimate the mean difference between these in this preserve. So the conditions that I have to check after I state everything, I have to state my shape. So the box plots do show skewness, and we said we were going to proceed with t procedures because our distribution it's actually exactly 30 if I remember correctly. Yep, n equals 30 for both of these. So we're going to assume that it's essentially symmetrical and normally distributed, but we're still using a t distribution. So it says, and I made a comment here, distributions of the trees may not be normal, but we're going to assume that they are essentially normal. Random sampling is stated, and then we can assume the 10% condition is met because there are probably more than 300 trees in each section of the forest, and we're not sampling more than 10%. When you run the confidence interval, so you go into the stat function in your calculator and you can go over to tests, and we're looking for a 2-sample t interval. So don't go to t-test, don't go to t-interval, we're doing a 2-sample t interval. So that is the 0 one here, 2-sample t interval. Again, if you need to pause, get your calculator out and follow along. You can do that. Now I'm going to input, not in the list function, but over here in the stats function. So I have to enter the information here. So I'm entering it, I set it up where my sample statistic here, number 1, is the northern half, and my 2 is the southern half. So I'm going to enter that 23.3, my standard deviation 17.5, and again, where am I getting these numbers? They're right here. They're already calculated for us. So scroll down a little bit so you can see. My sample size, I have to make sure I state. They're going to use that to get the degrees of freedom. So sample 2, 34.53. My standard deviation, number 2, is 14.26. Hope I wrote these down right. Yep. And my second sample size is also 30. So my confidence level, it does not state, oh, it does state, I'm sorry. So we're going to do a 90% confidence interval. Oops. This pooled thing here, just leave it as no for now. We can talk about it later. And calculate. So you may have already figured it out, but I just accidentally put in 23.3 for the test. So I'm just going to edit that. That should be 23.7. Sorry about that. And we should be able to go down and hit calculate, and then there we go. So that is how you can get the confidence interval. So again, just to review before I even look at how I wrote it out, this tells us that 90% of the time the mean difference between the north and the south trees should fall in this area. You know, we're 90% confident that the mean is in this range here. So what you should do for your work is you should write out what you put into the calculator. You don't have to draw a normal curve or show the formulas if you show this work. So if you do something dumb like I did and I put in the wrong number for a second and you'd written that down and moved on, as long as you show what your work is, you can still get partial credit. Now, the sentence here, we are 90% confident that the true mean difference north minus south in tree diameters is captured in this interval. I also made a comment that the interval is always negative, so the evidence suggests that northern trees are smaller. This is sort of getting into an inference that we make with hypothesis testing, but it was just a comment that I was making about that example. So that's how you do a confidence interval. It's the same as what we would normally do, same type of setup. Just make sure you don't mess up too bad on your calculator work. So moving on to significance tests. So significance tests for 2 different means. A lot of the same stuff, but I'm going to talk through it anyway. So we're looking for a difference between these 2 means and to see if that there's really enough of a difference that we would say one is different than the other. So this sentence right here is great because it really is a summary of what a hypothesis test or a significance test is. An observed difference between 2 sample means can reflect an actual difference in parameters, or it may just be due to chance in random sampling. So when we talk about type 1 and type 2 errors, we're talking about that chance in random sampling that is going to be a possibility always. So if we recognize that, we can still say that we are fairly confident that there is a difference between 2 different parameters. So the null hypothesis, we typically will set it up as one minus the other, and that difference is 0, being the null hypothesis. There is no difference in the 2 means. Or the alternate hypothesis, the is that there is a difference between the two means. So we can really skip right down to an example because all of the setup is going to be the same. The conditions are going to be the same. I'm just going to show you how to do it on the calculator so that you can set it up. Now, again, if you want to read the full question out, pause, read the question, make sure you understand it. I'm going to go straight into answering it because I've already read it, obviously. So the first thing you got to do is put these stats into your list function on the calculator. So you can go ahead and put those in. You can pause now while you put it in if you haven't done it yet. Ooh. All right, so good thing I double checked. I did make a mistake. You probably caught it as I was putting it in, but we should be all set to go now. So the question here, do the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo? So the mu1 is the mean decrease in blood pressure with calcium. So they make a note up here, don't get confused with the positive and negative. An increase appears as a negative number, so if we see this positive 18, that means a decrease of 18 millimeters of mercury. If we see this negative 3, that means an increase of 3. So just be careful with your negatives when you go to write your final sentences and stuff. So anyways, mu1, mean decrease with calcium, mean 2, mean decrease in blood pressure with the placebo. We're going to run a 2-sample t-test because, again, we do not know the population standard deviation. We are going to define our HO, our null hypothesis, as calcium minus placebo being no difference, and the alternate hypothesis as being calcium minus placebo making a difference, and that the calcium lowers it more than having a placebo. And then I define the mean difference as calcium minus placebo, so just make sure you define that. Now, the conditions, it says volunteers were participants if you go back up and read this. So that was a bit of a red flag for me. However, they were randomly assigned to the two groups. So for that reason, random assignment is actually happening in this case. Also, mu1 and mu2 have small sample sizes, the distributions for these. So really this should be your sample. I wrote the population here. Should have used better symbols here. So if I go and actually look at the stem plot, we can turn those on to see where I got these from. So if I go do that, I turn up the one with the outliers here, and then I'm going to go over to plot 2 here, and I'm going to turn that one on too. Plot 1 is my list 1, and then plot 2 is going to be on with list 2. So make sure it's not a scatter plot. So you're going to change this to list 2. So if you need to go back and watch that again, go for it. When you go to the graph, you see it's cut off a little bit. Go to your zoom and zoom stat, number 9, and it will take care of the stuff for you. If you are having a hard time with this background and you don't like the axes, you can go to the format and you should be able to turn it off, but I'm not going to do that. So I did a estimation comparing the two here just with a little tiny scale. This one is definitely symmetric. I mean, I guess you could say it's a little bit askew. This one, again, the sample size is so small that it's close enough. So we're going to say minor skewness, fairly symmetric shape. We're going to proceed with t-test procedures. Now here's a mistake I made, and I left it in here just to show you. So I said the 21 black men are less than 10% of the total population of black men. Now, the book was saying in this example you don't actually have to check the 10% condition because they weren't sampled, because they were volunteered in this study and everybody was taking part. So because you're not actually doing sampling, you don't have to check this 10% condition. So I know that's a little bit confusing, but you can also check back into the example in the book if you want more explanation for that. So moving forward, we run our test. So there's kind of two different ways you can do this. And if you check the green work here, I have the table method and the work for this. And then I also have the calculator method here, which is what I'm going to show with this example. So I go to stat, I go to test. Now I'm doing a 2-sample t-test. Not an interval, a test, because I'm doing a hypothesis test. I'm not going to go to the stats function like I did here last time. I'm going to go over to data, and I'm going to do list 1, list 2. The frequency here, just leave as 1. It just means that every item in the list happens one time. Now for your setup here, just make sure that you look back to your original hypothesis test. You said that you wanted to know if U1 or mu1 was larger than mu2, so I want to know if mu1 is larger than mu2, so that's what I'm going to set here. Again, we're going to hit no for pooled, don't worry about that, and we are going to calculate it. So there's a lot of stuff here, but it gives you the t-value. This t-value is the sample statistic that's calculated using the formula data point minus mean over standard deviation, 1.6037. Your p-value is about 6%, so we're going to make sure we write that down. And then degrees of freedom, again, this is doing a fancy formula here to reduce the increase the degrees of freedom. It's not really important that you know where that comes from. I know that one sample was 11 and one sample was 10, so you might think, to be safe, use the degrees of freedom of 9, which is what you would use if you were doing this with a table. But the calculator uses a formula to allow you to actually go up a little bit on degrees of freedom. And the more degrees of freedom you have, the less variation in that curve, so it actually gives you a little bit better, more accurate data. So anyways, write that out with the alpha value that you used. There was no, this is always going to run at a 95% confidence. So because the p-value is larger than the alpha value of 0.05, there is not statistical evidence to reject the null hypothesis and claim that the supplement reduces blood pressure. So if you read the example in the book, they said that this is real data, and the next time they ran the test, they just ran it with more people, and the p-value went down enough to show with confidence, yes, this calcium supplement does reduce blood pressure in black men. So it's important to realize the application of this real life wise is, like, just because the p-value is high doesn't mean that the test will never work. It just might mean that you need more people in your sample to eliminate the random variation in, having such a small sample size. So it's just important to know for your, if you're going to do this for real. So interpret the p-value. Again, this says p-value is assuming that your null hypothesis is true. The p-value is the probability that the difference in this blood pressure happens just by the chance involved with the random assignment of the test. So that means it's the chance that this test is wrong just because of the way they were randomly assigned. The more people you have, the less of a difference that makes, because one person being in one group, it doesn't make as much of a difference the more you have. So the way that you get this number, this part may be a little bit confusing to you. So this number is calculated from doing this mu1 minus mu2 based on the test. So if you go to your calculator and you look on the left of my screen, my average for the first group was a 5 milliliter reduction. For my second group, it was a 0.27 milliliter increase. So when you subtract these, right, mu1 minus mu2, or x sub 1 minus x sub 2, and you actually calculate that out, you do 5 minus a negative 0.273, and that gives you the true difference in the two groups. So that's what the true difference was in these groups, and then the 0.06 is the probability that this difference happens, or more, just based on random chance. So if you need to go back and listen to that again, do so. Cool, so we're almost done here. The next part here is just making sure that you're careful about which T procedures to use. So these two examples had two different types of procedures. So one is a paired test, and then one is where you have two groups of subjects. So the example that we just did with the calcium study for blood pressure, those were two groups of subjects, and then we measured one group and measured the other group. So that's a two sample test, because you're you're testing two different samples. It's not like the group that got the placebo also got the calcium test. So that's a two-sample t-test. A paired t-test is another type of example where both groups get both treatments. So we're going to look at an example of each here. So you can see the answers here, but basically I'm going to explain the reasons. So this first test, it's asking you to decide, do you use T procedures for pairs or two-sample T procedures? So to test wear characteristics of two tire brands, A and B, A is mounted on the side of each car in the rear, B is mounted on the other side. Which side gets which brand is determined by flipping a coin. So the car gets both tires. So it's a paired test because you're able to test the two tires against each other in a controlled environment with everything else being the same. So that's a paired T procedure. So in the example down here, when you're talking about listening to music to increase productivity, 20 factory workers agree to take part in a study. They randomly assign 10 workers to do one task with music and 10 workers to do the task in silence. So it's not like you're testing one worker before and one worker after. You're just randomly testing one group versus the other group. Every worker does not get both treatments, so this is a two-sample T inference because we're measuring differences between the two groups. So hope this was helpful, and feel free to post some questions. But that is the 10-2 notes.